Now we look at this problem about the related rates. So we know that a boat is put into a dock by a rope attached to the bow of the boat and passing through a pulley on the dock that is 1 meter higher than the bow of the boat. So basically we can draw a diagram or picture. So this is the boat, and we have a bow here, and we also have the dock here. So this is dock, and we have a pulley 1 meter higher. So this is part is 1 meter, and we have this red triangle. Okay, and the rope is put in this direction. So we want to know that if the rope is put in at a rate of 2 meters per second, how fast is the boat approaching to the dock when it is 8 meters from the dock? Okay, so basically in this right triangle, so I'm going to redraw it here. We have a right triangle, and we want to know that when the distance between the boat and the dock is 8 meters, that means this side is equal to 8 meters, and this side is 1 meter because it is a pulley, which is 1 meter higher than the dock. And we want to know how fast that is, the rate of the boat approaching to the dock. Okay, so basically we want to find this rate here. Alright, now because we have a right triangle, if we let this side to be x, because it is always changing, and this hypotenuse to be y, by the Pythagorean theorem, we can get a relationship between x and y, which is y squared, that is the hypotenuse square, equal to x squared plus 1 squared, which is just 1. Okay? Alright. Now, because both x and y are changing with time, so basically both x and y are the function of t. So here x and y function of t, of the time. And then we're going to differentiate this equation with respect to the time t. So by the either product rule or some formula you can use from the lecture, you know if you take the derivative of this equation with respect to t, you will have 2y times dy over dt equal to 2x times dx over dt, and plus 1. If you take the derivative of 1 with respect to time, it is just 0. Okay? Alright, so basically in this problem we want to find how fast is the boat approaching to the dock. So that is, we want to find dx over dt. That is this arrow here. Okay? So that means to solve for dx over dt, we need to know several quantities. That is y, dy over dt, and x. Well, I mean, x is easy to find because from the problem we know that x is equal to 8. So x equal to 8. But what can you say about y and the dy over dt? So remember, we are in a right triangle, and we can use the Pythagorean theorem to find y. That is given by the square root of 8 squared plus 1 squared. If you calculate this out, it is root 65. And for the last quantity, which is dy over dt, it is also easy because we know that the rope is pulled in the rate of 2 meters per second. That means dy over dt is equal to 2. Okay, now we plug in all the numbers into this equation. We have 2 times y, that is root 65, times dy over dt, that's this 2, equal to 2 times x, that is 8, times dx over dt. Okay, now if we solve it, we will have dx over dt equal to root 65 over 4 meters per second, and this is about 2.2 meters per second. Okay, this will be our final result. Okay, this is the first part. Then let's go to the second part. We want to know at this moment how fast is the angle between the rope and the horizontal line from the bow of the boat to the dock changing. Okay, again, I'm going to draw a diagram. So remember, we have a right triangle like this, and we'd assume this hypotenuse is y, and this side is x. And remember, this side has 1. Okay, so the angle between the rope and the horizontal line is this angle here. And I'm going to let this angle to be theta. Okay, so by using your knowledge of trigonometry, we know that tangent of theta is equal to its opposite, that is 1, divided by its adjacent, that is x. So basically we have tangent theta equal to 1 over x. Okay, you may ask why I choose tangent instead of other trigonometric functions. That is because all the others will depend on y, and y is another function of x. So basically we can just use tangent and only use x instead of using y to simplify our problem. Okay, so we can multiply both sides by x. For this equation, we have x times tangent theta equal to 1. And here, remember that x is changing, theta is also changing with respect to time. So again, I'm going to differentiate this function with respect to time t. And because it is the product of two functions, so I'm going to use the product rule. So I'm going to firstly differentiate with of x with respect to t, that is dx over dt times tangent theta, and then keep x and differentiate tangent theta. So remember, the derivative of tangent function is secant square, so I will have x times secant square of theta. And also remember, theta is a function in terms of t, so by the chain rule, I will have d theta over dt equal to the derivative of 1 is just 0. Okay? So now, because we want to know the change rate of the angle, that means this part, d theta over dt, is the quantity we want to find. To solve this problem, we need to know dx over dt, tangent theta, x, and a secant theta square. Okay? Again, we're considering about when x equal to 8, so we will know x equal to 8. And by the part A, we know dx over dt is equal to root 65 over 4. And when x equal to 8, we know that tangent theta is equal to 1 over 8. And by solving the triangle, we can find that the secant theta is equal to root 65 over 8. So that means secant theta square is equal to 65 over 64. Okay, now we're going to plug all the quantities into this equation and solve it. So we have dx over dt is equal to root 65 over 4 times tangent theta, which is 1 over 8, plus x is 8 times secant square, that is 65 over 64 times the theta over dt equal to 0. Okay, so actually we can simplify the algebra a little bit. So that is, the first part is this product, that is root 65 over 32 plus 8, and the 64 in the denominator can be cancelled a little bit, that is 65 over 8 times the theta over dt. And finally, if we solve it, that means this theta over dt is equal to negative 1 over 4 times root 65. And here, the unit is radians per second. Okay, and this will be our final result. Okay, this is everything about this problem.